The p-value approach is the second approach that we'll learn for hypothesis testing. The p-value is the probability, assuming our null hypothesis is true, of getting a test statistic at least as extreme as the test statistic we calculate from our sample. This is also known as the observed significance level. So here is the decision rule that we'll be using. There is only one decision rule, in that if our p-value is less than our alpha, we reject the null. If our p-value that we find is greater or equal to the alpha value, we do not reject the null. This process gives us more information than the critical value approach, although they are related. Recall I described the critical value approach is like taking a class as pass or fail. The p-value approach tells you how strongly you will reject or accept a decision. It's like taking a class for a grade, where an A is a strong class grade and an F is a poor class grade. Thus, the farther away our p-value is from the alpha value, the stronger the decision. So we'll use problem 4 in the textbook. Compute the p-value, assuming that the hypothesis test is a one-tailed test. So you can see we've got a one-tailed test in the upper tail and a one-tailed test in the lower tail that we're going to be practicing. And you're going to use Appendix D. Essentially, our p-value is the area of our rejection zone. So before, with the critical value approach, you were just trying to find the cutoff point, this line right here. But now with the p-value approach, you're trying to find the area of the rejection zone. That's how they're related. So going to our Appendix D, we first look for the 2.09, where the 2.0 is on the left side of the appendix, and the 0.09 is in the column. So when we read our Appendix D, 2.09 shows 0.4817, because recall, Appendix D tells us the area from the middle out to our z-value. I don't want to know this area right here. I want to know what's in the shaded area. So in order to find this, because I know half my curve is worth 0.5, I'm going to subtract what I know from Appendix D from 0.5 to get my shaded area right here. So 0.5 minus 0.4817 is 0.0183. In other words, our p-value for this shaded area is 0.0183. And then I would take that p-value and compare it to my alpha value. So say my alpha value is 0.05. Because my p-value is smaller than 0.05, meaning it's out here in the rejection region, that means the shaded area of my sample size is so small it's over here. That means we would reject the null. Let's do part B. Say our z-value is negative 1.55. Again, I go to the Appendix D, I look on the left for 1.5, and then I go out to the column where it says 0.05, or my 5 is in the second decimal place. That will give me a value in the table at 0.4394. Again, because the z-value in our Appendix D tells us from the middle out to the z-value. So that's this area right here. But again, I don't want to know this area. I want to know the shaded region. So because I know half my curve is worth 0.5, and my appendix gave me this value of right here of 0.4394 when our z-value is negative 1.55, that means our shaded area is 0.0606. Now again, if we compare our p-value to our cutoff point, say our alpha value is 0.05, meaning my 0.05 starts somewhere over here, we can see that 0.0606 is greater than 0.05. That means we do not reject the null because my p-value is bigger than my alpha value. But we really just wanted to make sure in this problem you understood how to find the shaded area for our particular p-value. This is problem 6 in the textbook. Here's a one-tailed test. And how we know it's a one-tailed test is looking at the alternative hypothesis. This greater than in the alternative hypothesis means it's an upper-tailed test. Recall, looking at our greater than symbol points to the right side of our curve. So we know it's on the upper side. So for our decision rule, we will reject the null if the calculated value of our test statistic z is greater than the critical value. The reason why we know it's greater than is because the greater than symbol in our alternative hypothesis. So just remember, our alternative hypothesis symbol is going to tell us our decision rule. And now, how do we find our critical value? I picked this problem because it turns out we do not have the critical value showing in Appendix F. So you'll have to use Excel. In Excel, you would type in equals norm.s.inv parentheses 1 minus our alpha value of 0.02. And that will give us a critical value of 2.05. So this is our cutoff point. If our test statistic z is greater than our critical value of 2.05, we will reject the null. If it's not, we will not reject it. So now we want to calculate our value of the test statistic. Again, you know how to do this. We'll plug in our sample mean given to us right here of 47.1 minus our hypothesized population mean of 45. We'll plug in our known population standard deviation of 9. And again, if you see this sigma symbol, that means we know the population standard deviation. And then we'll plug in our sample size of 80 into the square root. So when we subtract 47.1 minus 45 for our sampling error, we get 2.1. And when we calculate our standard error by taking 9 divided by the square root of 80, we get 1.006. Dividing the numerator by the denominator, we get a calculated test statistic of 2.09. Before I make any decisions, I also want us to practice the p-value approach, which we just did in problem 4 earlier. So to find our p-value for the test statistic of 2.09, I go to my Appendix D, and I see that 2.09 is worth 0.4817. And we have to subtract it from half of our curve of 0.5 to get the area in the tail, which is 0.0183. Again, this should look familiar because you just did this on the previous slide. I'm just using it here in this example so you can see how it all gets put together. Now let's make our conclusions. If we use the critical value approach, what you'll do is you'll compare the number in part B to the number in part A. So because our test statistic z of 2.09 is greater than our critical value or our cutoff point of 2.05, we reject the null. And if you forget why we say this, you can always go back to the decision rule and read it out loud of what our decision rule is going to tell us how to make our decision. Similarly, if I decide, hey, let's use the p-value approach, here's my p-value, and I'm going to compare that to my alpha value. So for the p-value approach, because of my p-value that I found with the Appendix D is 0.0183, and that number is less than our alpha value of 0.02, right here given to us in our story, we reject the null. Because remember, our decision rule with p-values is that if our p-value is less than our alpha, we reject the null. Note that both our critical value approach and our p-value approach gave us the same decision. We reject the null. That means our alternative hypothesis that our population mean is greater than 45 is true. The critical value approach and the p-value approach will always have the same decision because it's based on the same information. We're using the same alpha, we've got our same test statistic, and so if you ever do both processes and they don't match, you know there's an error somewhere in your decision-making process. So really, hypothesis testing is a combination of math you already know that you learned in the previous chapters. That's why it was so important really to get that foundation. But now we're applying critical thinking in our decision making, where we're comparing our data to decide whether or not to reject the null.